It's just a quick introduction here. Myself, I am Ian Hutt. I am the Associate Director that leads our System Studies group here at Commonwealth. We cover power system studies in all sorts of arenas. We cover things for interconnection support, system planning and transmission planning, and distribution planning. So if there's any support there, we have our whole team of system studies experts and engineers that can assist you with that. We also cover studies that support our design projects. So power gen, substation, transmission. We're able to provide the whole gamut of studies to support your projects, both for generation related projects, data center large load projects, industrial, distribution and transmission. We have special expertise in EMF studies, both for station and for transmission lines. So if that comes up, we can assist you as well. And also for NERC compliance. So as we see more and more NERC rules and some major NERC changes happening this year and next year, if there's any support there as well, feel free to reach out. A little bit about me. I have 2 degrees from Central Michigan University, electrical engineer. Been working in system studies for over 20 years, and also I'm licensed in 7 states. Also presenting today is Joe Johnson. He is a Michigan Tech grad from 2015. He has over 10 years in system studies and relay settings experience in the industry and is licensed here in Michigan. And we're going to start off with a question. So just trying to get a feel for the crowd here on where your area of expertise is when it comes to installation coordination. So we're going to pull up a poll here. So get your clickers out. And as soon as all's ready, so just put your answers in. Just how familiar are you with installation coordination? And now those polls come up. We see there's quite a few people on the call here that have worked with the equipment, with arresters and insulators. So 37 responses. We'll give it just a minute here, see if any more. And I know there's a few that haven't really played in this arena yet. So we'll make sure that we cover these topics in a way that both work for those that are somewhat familiar and that have some experience as well. So I think you'll find this enlightening. All right. And Joe, take it away.
All right. So first thing, for those people who have no familiarity, well, what is installation coordination? Well, the actual definition from some of the standards is the selection of the installation strength of equipment in relation to the voltages which can appear on the system for which equipment is intended, and taking into account the service environment and the characteristics of the available protective devices. What does that really mean? That means, how do we make sure our transformers and breakers and buses that cost millions of dollars and take months and months or years to install and procure, how do we make sure we don't break those because of system conditions? The system out there, it's not just 115 kV line doesn't stay at 115 kV all the time. There's all kinds of stresses and lightning strikes, switching surges, things will go into, as well as faults and voltage rise and fall because of those things. It's anything but static. It's these extreme events. How do we make sure our equipment is protected? So just starting off, what are the types of insulation? There are 2 types of insulation. One is called self-restoring insulation. This is air gaps that are outside of the equipment, right? Those sacks of insulators you see on all of the substations, that's really an air gap there. And when you have an arc and you see an arc, that's ionized the air, and the air is effectively becoming a path for electricity. It's significantly lower than a normal breakdown of air. And when that arc is extinguished by whatever means, the breaker opens, your protective devices interrupt that, the new air rushes in and replaces the old air, the ionization goes away, and that insulation returns to its former glory. It's now just as good as it was before. Typically no damage, unless it's your protection maybe didn't interrupt fast enough, but no real damage here. Non-self-restoring insulation is the insulation that can be more on the inside, not necessarily inside of devices, but oil immersed transformers, breakers inside of the actual breaker device. There's gases and there's oils in these pieces of equipment. And if there's an arc inside of that, well, those aren't readily replaced by more oil around them necessarily. You get a degradation of that medium. And so best case, eventually you need to replace it, maybe even after one event, maybe you can survive a couple events. Worst case, you have damage internally to the equipment and a severe degradation of the protection of that insulating medium. Speaking of those failure modes, I just want to go into what we're going to talk about. We're going to be talking about a lot of different wave types here, talking about arresters and how they protect. When you see all of these things, it's not like we're designing a system that's invincible and invulnerable. There's always a chance of flashover. It's kind of almost an example of chaos. There's not really a good way to determine if you're going to flash over or if you're not. You just set yourself up for the best chance of success. So in terms of that probability, aim for about 1% to 2% flashover probability per event. And that's for self-restoring insulation or external insulation. So that's based on 2 tests with 15 and 10 shots. The 15-shot test, basically 15 different waves that we create in the lab. We don't actually go out and hold up a lightning rod and make sure something comes in. When we test our equipment that way, we generate a wave and send 15 or 10 of them, and the 15 shot is able to have up to 2 failures, and the 10 shot is able to have up to 1 failure. I have always been bad at stats. I have no idea how that equals 1% to 2%, but apparently it does. Another failure mode is anecdotally about 80 to 90% of arrestor failures result in a short circuit. So if you have a case where your arrestor is it's beat down, long temporary overvoltage, a lot of lightning strikes, a big switching surge or several in a row, most of the time you're going to fail. It's going to fail into a short, and that's going to effectively look like a fault, and your system won't necessarily be unprotected during those times because you have a broken arrestor, but that arrestor also becomes a fault. So how do we actually classify these insulations and the levels there? Well, that's BIL and BSL. So BIL is the basic lightning impulse insulation level. That's actually BLIIL. I have no idea who came up with that acronym, but it looks nice. BSL is the basic switching level. So basic lightning level, that is for lightning events, and basic switching level, that's for switching events. There's standard sizes based on your voltage. These are not necessarily something you come in and pick your own voltage. There's standard classes. These involve separation distances, clearances. They're built in with all of those considerations for that voltage level into the BIL and BSL. These are usually selected very early in the design, and that's to size the equipment. Sometimes we don't even necessarily have time to really dig in on these studies. And with the way that the industry is going and having lead time be about the most important thing now, even cases where just shut up and take my money, get it done as fast as you can. That's a lot of the cases we're seeing. We're generally going a little bit more conservative just to make sure that we don't have any surprises later in the project and have to reorder something. Just as a note, the BIL is really the most important. It dominates for voltages up to EHV, before 345 kV, and then BSL becomes important beyond EHV or 345 kV and above. That's because the switching surges really scale with the voltage more so than the lightning will, and also the longer duration of these switching events leads to much more energy being discharged because of their wave profile, which we will look at going forward. So what are these cases that we're protecting for? We're protecting for lightning strikes and switching surges primarily. The lightning strikes can enter a substation anywhere from 200 kV to 2.5 megavolts. When they actually strike a line, you can see surges or voltages at around 15 to 17 megavolts potentially, but by the time they've reached the substation, they've gone through some impedance, they've attenuated down, they've reflected, which we'll all get into things like this later, but they generally are a lower magnitude once they actually enter the substation. A switching surge can be 1.2 to 3 per unit voltage, which is why as you start getting up to those higher voltages, you're getting a multiplier on your voltage, which is why switching becomes much more impactful at the higher voltage levels. Well, what do these look like? These are traveling waves. So a traveling wave is basically created when a lightning strike or switching surge happens because there is a very rapid change in current across an impedance over a short amount of time. When a lightning strike happens, you're getting a very large amount of current injected into your line across an impedance, so very large voltage spike. When a switching surge happens, that's when a breaker opens and there's a small amount of chopping current. Even a small amount of chopping current going from something to zero almost instantly causes a very big voltage spike. Again, these are traveling waves. They propagate usually in both directions from their point of inception. And we're going to go over these, and there's two important values in how we test these. There's the time to crest and the time to half. So you'll see a number slash another number and then a time step, which is usually microseconds. And that's what that means. The first number is the time from the very beginning of the wave until it hits its peak. And the second number is till it gets back to half of the value back down to the before the wave value. Just as a little informational graphic here, this is the average lightning strikes per year from 2015 to 2019, some of the latest data I could find. So cases where you're worried about lightning, more of those lower voltage situations, if you're in Florida or Texas, then you really need to worry about it a lot more. Whereas maybe out in the Pacific Northwest and California, it's not as big of a deal. Always make sure that you're not just designing your site for whatever the worst case is, because you can overbuild. Make sure to have some understanding of where you are in the system that you're actually, or the area you're working with, to make sure you design appropriately. So just talking about these waves now, these are the test waves that we do. I mentioned those before. We can't necessarily recreate a lightning bolt. We're not going to go out and make that happen. We're not going to open a bunch of breakers and see what waves hit it and test equipment that way. In a lab, we create these waves, and these are the waves that more closely resemble what we would expect to see. So the first is a front of wave. That's the extreme wave steepness test. That is a zero to crest time of half a microsecond. So that basically is a test to see how individual portions and the weakest portion of insulation can actually withstand, because this wave is rising so fast that the voltage doesn't actually have time to balance across the insulation. It kind of gets stressed at a single point of insulation. That's about how you're going to see your biggest point of failure for individual points of insulation along your conductor or insulator stack. The next is the lightning impulse withstand level. That is to simulate a lightning strike, and that is a 1.2 microsecond rise time. It's a little bit slower, but still crazy fast. This is microseconds. And then you have the switching impulse withstand level for switching events. As you can see, that is a significantly slower compared to the other two events. So if you imagine the amount of energy that's in that wave, imagine the integral of the area underneath is really the power that's being delivered. So that's why these switching impulses can be very significant, because they're much longer duration and have a lot of energy behind them. As a note, these are for the equipment themselves, for things like transformers, buses, breakers, and these are the waves for arrestor capabilities. So there's a current impulse test used for arresters, and that is a 8 microsecond time to crest for lightning, and a 30 or 45 microsecond time to crest for switching. So you can see in this diagram here, there's several different waves. You have your front of wave, very steep, your voltage discharge up here about as steep as it gets at the highest peak, and you see different voltage and current discharge values depending on the wave type. You can see the lightning is significantly faster rise and then falls off, whereas the switch hasn't even really begun to hit its peak by the time lightning's fallen off. A lot more energy is actually underneath the switching wave usually. An important note, and we'll get into this later, these waves are also associated with current values, and these are we'll get into later when we get into arrestor data sheets. These are basically a magnitude of the current coming in on that wave. Generally, we try to size it for the most conservative. This can go from anywhere from 5 to 40 Ka, and switching 500 to 1,000, 2,000 amps. So another question, how fast do traveling waves move? No cheating. You can see the answers maybe. I think. I don't know if they can see them yet, but
For anyone who's looking for it, the poll can be taken also within the chat. All right, we got about 35 responses. 33% looks like the leading amount, but okay, Joe, back to you.
All right. So the correct answer is 300 meters per microsecond. So traveling waves move at about 98% of the speed of light. So the first answer there, that was 1,000 feet per second. That's sound at standard temperature and pressure. And that last answer, 500 meters per second, is faster than light. So Einstein says that's not possible. But 300 meters per second for that half microsecond front of wave, one of our fastest waves, that's 150 meters from where the wave starts till it hits its peak. And so for us Americans, that's about 5 blue whales, because anything but the metric system. And the problem with this medium is I have no idea if that joke landed or not, so I'm just going to hand it off to Ian, and he can talk about arresters.
I don't know, I'm smiling, Joe. I love it. So anything but the metric system for us Americans, right? So it is a little wild just to think about that. Like, so when these lightning strikes happen, I always thought of it as like a voltage impulse that was very localized, but that's really not the case. I mean, these things are waves that are traveling at incredible speeds over incredible distances and building as they go, right? So I always thought that was it helps visualize it. It makes sense when you think about it. So but yeah, just unique to get that insight. Thank you, Joe. So this slide here is on. I'm just talking about the equipment. What are we using out there to deal with this problem, right? So we want to make sure that these big traveling waves that we just talked about aren't coming into our equipment and breaking down our insulation. It's a big problem, right? But luckily we have a solution here. So we have these arresters. What we're seeing on the slide here is a standard station class arrestor with the Corona halo on it. So essentially what it is, it's kind of like a transistor in a way that when it's at a, you know, when we have nominal voltages, things that we expect and that we have, that this device is rated for, there is a small amount of current, microamps, that's going through this device. But just a small amount. It's essentially allowing the system to do its thing. It's allowing the voltages to be out there. But the minute we see voltage spikes in its operate range, this thing goes from conducting a small amount of current to being a pretty low impedance path to ground. And by doing that, it clamps that voltage down, and it can do this very, very, very quickly. So by doing that, when these transients come, voltage spikes, lightning strikes, and surging events for switching, then these devices can operate, they can clamp voltage and help protect our equipment that's in the vicinity. So, you know, just talking about the different types of applications, you know, we're really focused on, for this presentation, on lightning and switching events. However, there are other events that happen on the system, maybe called temporary overvoltages. This is when you may have a fault that's driving voltages to higher levels. We won't cover it too much here, but just as a note, these arresters will activate and operate for all voltage levels that are within their operate range. So if we have a fault that drives the unfaulted phases to higher voltages based on grounding conditions and grounding types of a system, these arresters may operate as well. And it is a consideration when you're thinking about sizing this equipment. A couple things. When it comes to arresters, there's two main quantities that we're really trying to specify. And this might be something that we have to do very early on in the project, just like Joe mentioned. Lead times have gotten severe across the industry. Even getting arresters sometimes has been challenging in a timely manner. So generally, we want to know what voltage class we need before we go in, so we can get this equipment ordered. That's something that we've been seeing more and more. The two quantities that we're really focused on here is the MCOV rating of the arresters and also the energy rating. You know, what amount of energy can these arresters withstand? And we'll follow up with another question here. So we'll have Dell bring the poll up for us. Just a couple for a system, just an arbitrary system. If we're at 230 kV, this is a standard transmission voltage we see across the industry, which I'll remind you is 133 kV line to ground. What would be an appropriate MCOV rating for an arrestor? We'll bring the poll up and we'll wait to see your responses.
And just so everyone knows, this is not something that you missed. This is a before you learn a question. So don't feel bad about taking a guess here.
Yeah, no worries. Yep, no wrong answers. Well, if there is, we won't berate you for it. I promise. So, all right, what do we got? All right, your response is coming in.
I'm not sure if you see it, but it looks like 140 kV with the most responses.
You're getting a lot more responses on this one. Wow.
Sure.
All right. Yeah, it's like 51 responses. The answer is anything 140 kV and above. Now, above with an asterisk, there's a limit. You can't go too big because otherwise it won't work. But we're about to go in and look at the needs of the site. A smaller arrestor closer to the actual line to ground voltage has more risk of conducting more during these TOV events, as Ian was mentioning. And if it's below 133 kV, which are options 1 and 2, you actually will be conducting at normal system voltage, and your arrestor will be conducting continuously, and it's not going to last very long. 140 is just above that, but I've seen many cases where 160, even 180 would be used in this case. These aren't necessarily standard classes, by the way. It was just a thought exercise, but these arrestors can be size greater. They just have higher residual voltages, which we'll also go into, and the consideration there of how much protection margin are you sacrificing, and at the same time, the benefit of that is you don't need as much energy rating because they're not going to operate as regularly during TOV events. So this is speaking of TOV, this is a slide that the TOV curve, and I'll pass it back to Ian to explain this.
Yeah, thank you, Joe. So, talking about TOV, and again, we're not going to get too deep, but just kind of touch on it high level because it is related to arrestor selection and sizing. TOV is very sensitive to time. So, how long will these TOV events last? And this kind of goes into protection. So, when we talk about protection margins, generally we try to think in the realm of a few cycles to maybe up to 2 to 10 cycles, depending on your protection, your schemes, your backup protection levels, and breaker failure events, things like that. So we can kind of see a couple of looks here. If you look at this graph, you can notice that it's a log graph with time as your x-axis, and we have a voltage as your y-axis. But note that voltage isn't per unit as nominal voltage; it's your MCOV per unit. So note that your nominal voltage will likely be slightly less, just like we discussed in our question. Your MCOV rating needs to be above your nominal rating on a line to ground value. And then depending on how big that value is, depends a little bit on your application, your margins, and some other things that might come out of your installation coordination studies. But you'll note that for shorter duration times, you can have a higher voltage that's allowed with these TOV events. You'll also notice on this graph that there's two different curves. One is for new arrestors without any duty. This is what you might expect during testing phases when we're looking at new equipment. However, we have to understand that these devices, as they work, as they take more and more strikes, they degrade. So as that degradation happens, we have that classified as well as the prior duty line that we're seeing there. So you'll notice that as long as your protection is guaranteed within a certain window of time, you can note that, okay, in our green box that we have here, that we have a per unit MCOV of 1.3 is allowed. And, that'll work even after these devices have seen a fair amount of action. However, if our clearing times go higher because of protection, because of schemes and other things, we'll notice that, that per unit MCOV value will drop for TOV concerns. And this is a graph that we'll see for most equipment that's out there.
Thanks, Ian. I just want to continue talking a few more things. This is a very arrestor heavy presentation, but that's like Ian was saying before, this is a large part of what the discipline is. So arrestors are single phase devices, so they get compared to line to ground voltages in that exercise we did before. The TOV considerations, we talked about those. We're going to be getting into something called a voltage current curve. It's a VI or UI curve. And that is going to show the non-ideal relationship between voltage and current. Sorry, non-linear, I should say. And then we're going to do a example calculation using residual voltage for the different wave types and kind of show how we get these protective margins based on some of the standards. And one important note is a lot of times you'll see a duty cycle come up if you're working on speccing these pieces of equipment, even to the point of you'll see something that's a 24.4 kV MCOV, but a 30 kV duty cycle. Even the part number will have -30 in it because it's the old way of doing things. Duty cycle has been replaced by MCOV, and it's a potential pitfall if you think you're speccing something at 24.4 kV MCOV and you order the duty cycle, that's going to be too small. Whereas vice versa, if you think you're speccing the duty cycle and you pick an MCOV of that value, it could be too large. It's really important to pay attention to the differences between those. I have seen that a few times where those have been selected incorrectly. So last little bit on arresters. They are just like any other piece of equipment. They have short circuit withstand limits. They have other considerations, just like any other piece of equipment. And there's three classes that we really work with. That is station, intermediate, and distribution class. So these have different MCOV ranges, different impulse current limits, and that's, you know, when you have the switching events or you have the lightning events, and then the minimum thermal limits. So, you know, a station class is going to have generally higher amounts of thermal limits to be considered a station class. And those thermal limits, again, are that energy rating, that kJ per kV MCOV, or Q for coulombs. There's two ways of doing it. Sometimes it's requested to do it in coulombs. Sometimes it's requested to do it in kilojoules. It's really kind of a dealer's choice on whoever's going to be reviewing your work. So this is a data sheet. There's a lot of data here. I'm not going to go into all of it, but I just want to point out a few key things. This is a 345 kV arrestor with a 1300 kV BIL. Skipping over this real quick, we can see over here we have a lightning impulse withstand voltage with that previously called out waveform of both switching and lightning, actually. So this is the BIL, and the 850 is the BSL. We see some temporary overvoltage. It's not a graph, but it's a couple of points on the graph. Lots of mechanical data here, which we are not going to get into. But the really important thing about the arrestor is in this section. We can see its MCOV is 220 kV. And we start seeing these wave types we were talking about before. This 1.5 is the front of wave. Before I said that was half cycle, or half microsecond, but those really just kind of the typical ones we use to test. You could use other ones to test, and there's kind of ranges that are described in the standards. So there's a little bit of wiggle room, but basically when you're at 1 or less microsecond, that's a front of wave. An 8 microsecond is a lightning, and a 30 or 45 is a switching event. So as I mentioned before too, you can see these are all lightning events, these 8/20s. They go from 5 Ka up to 40 Ka. Well, what does this mean? Well, we see at a 5 Ka lightning strike with that speed, we get these voltages, and these are what's called residual voltages. The arrestor is going to see this wave come in, and it's going to clamp the voltage, but it's not ideal. It's not going to maintain and only let 750 kV through every time, or 550 kV through every time. Depending on the wave steepness, its rate of rise, a bunch of very advanced things that determine wave speed, wave steepness. They will determine how much energy is actually let through the arrestor. And so that's what these tests are meant to show. Generally, in my studies that I perform, I go most conservative. Is it likely that you're going to have 40 Ka lightning strikes? Not necessarily, but like I said before, lead time is important. You don't want to order the wrong part. Just be conservative from the beginning, and the price differences here aren't necessarily too extreme. So just to point out some values we're going to be using coming up, we're going to be using this front of wave, worst case, 750 kV. We're going to be using this lightning wave, 762 kV, and we're going to be using this switching wave, 552 kV. So using C62.22 is a great method of figuring out if you're sized appropriately and you have correct protective margins. Reminder, this is a 1300 kV BIL system and a 220 kV MCOV arrestor. So there are three real equations. This is a specific kind of example we're giving here, there's all kinds of permutations on how these equations work, what values are used depending on the number of lines coming into the system, the number of transformers in the system. This is kind of a general introduction. There's a lot of material. I highly recommend reading into the standard if you want to learn more about specifically testing your case. But these equations are the protective ratios of lightning 1, protective ratio of lightning 2, and the protective ratio of switching. So the first one, PRL1, uses chop wave withstand for breakers and front of wave rating for transformers. And that's very confusing because there's a front of wave rating and there's a front of wave. So it's kind of confusing, but once you dig into it, it starts to make sense. These ratings are multiples of BIL. Again, I generally go more conservative when I do these just to make sure everything's sized appropriately. It's about 1.3 times the BIL is the chop wave withstand in this case. So 1.3 times 1300 kV, that's 1690 kV. And then that was divided by the residual voltage that we had from our front of wave previously, which was that 750. That equals 225%, but the margin is 125%. So the suggested value in C62.22 is 20%. So this is exceeded. Then for the protective ratio lightning 2, that is the BIL over the lightning protective level, which is your lightning impulse. So that is the 1300 kV divided by the 762 kV that we saw, 70.6 margin with 20% suggested. And then switching the BSL over the switching protective level, which was that 2 Ka 45/90 microsecond wave. That's 552 kV, 54% margin with a 15% suggested. So this is massively oversized from this perspective. Now, there's reasons you might want this. You know for sure that arrestor is sized appropriately because you have plenty of margin. You are able to potentially get different arresters that come in closer, and maybe you think you're not spending as much money on an overbuilt arrestor, but that's not necessarily the case here because the amount of time you spend on this and the price at the price point these are, it's usually just these are pretty standard. It kind of slots right in, and this is kind of more of a formality in verifying, yes, we are coordinating. So one thing about these arresters as well is the separation distance. So the distance between your protected equipment and your arrestor does matter. But these waves are, again, like I said, chaotic. They have a lot of energy behind them. There's attenuations, reflections, surge impedances, all these different things come together, and they can effectively allow a wave to re-steepen and recover once it's past the arrestor, because the arrestor is only clamping its voltage at its own terminals. Once it's past, the wave starts to change back into its former glory sometimes. And if you're too far away, that wave has too much physical distance to actually reform, and it can now exceed your protective, your insulation at your equipment. So again, these equations for this separation distance allowable, taking the BIL, the wave steepness, the arrestor lead lengths, and there's Annex C of C62.22 explains how this works. It's fairly complicated equations that I've noticed have some corner cases that don't always work. So there is a very handy table, but it's only for single line, single transformer stations. So it doesn't necessarily help you. This is probably one of the more complex equations in this standard that I've seen. But it's again, a very important aspect. You can't just have an arrestor, a mile away and think it's going to protect your transformer. It doesn't work like that. One important note that sorry, this is not working right. Actually, never mind. Sorry, Luna. Ian?
Yep, here we go. So question here. So talking about these protection margins, we want to talk about what do we have here? What mitigation steps do we have to improve our performance when we get into situations where maybe performance is a concern here? Maybe we're close to margins and we want to get maybe more margin on those acceptable margins, or just beat them alone. So this is a pick 3 on this one. So pick the 3 that you think is going to make the difference. So do we decrease or increase the separation distance? Do we use a lower or higher MCOV arrestor? Or do we increase or decrease the BIL level of the equipment? All right, responses coming in. You can see that in the chat. And as we go forward, we'll notice as we come in, where are we at? We got 41 responses. We can see decrease over increase. We can see higher MCOB over lower MCOB, and higher BIL over lower BIL. So the popular answers are correct in this instance.
They are not in this instance, actually. So
Oh, it's the
the
MCOB.
correct
Yeah,
answer,
there it is.
the
Yeah.
correct answer is decrease the separation distance, use a lower MCOB, and increase the BIL. So we talked before about that. The lower separation distance can allow for these lower protection margins, right? Generally, you're going to see that 220 kV MCOB had those associated residual voltages we were looking at. Well, a 200 kV would typically have lower residual voltages as well. And those are the denominator, so you're dividing by that smaller number and you get more margin. There are risks to this. If you go too low, potentially you need to step up the energy class, or maybe you can't even get an energy class that's strong enough. So this isn't necessarily an all-encompassing answer, but that is one of your options. So the higher BIL and BSL also, that just basically says your equipment is able to handle a bigger spike of voltage. And so that is one of the ways too, you're increasing your numerator in that case. So yeah, 1, 3, and 5. Mentioned before, we were to mention the UI VI curve. This is a VI characteristic of an arrestor. There's a lot going on here, so let's kind of break it down. In this region here, this is our normal operating region, and this is where we just start getting into TOB. So we see very, very small microamps of current flowing at these voltages, and this is happening all the time, always flowing microamps through these arrestors. And then as you start seeing the rise in voltage, you hit this knee point where a very small amount of increase in voltage is a very orders of magnitude increase in current. I mean, from just this small increase here in voltage goes from 0.001 amps to 10 amps. And this is your TOB region that we were talking about before. These curves are not necessarily fit to look at long-term discharge levels. These are more of a fast event. So this isn't necessarily behavior for seconds, but it does show an instantaneous behavior of the arrestor. Once you get into your switching surge region, you get to these, they're still lower than lightning impulse, but they last a lot longer. So imagine an impulse that's only 1/10 of the current, but potentially 20 times as long. It'll carry a lot more energy. And then we get up into lightning impulse region, where we actually start to see the behavior start to fall off and be a little bit more voltage dependent on the current increase. So the last thing I wanted to talk about is what is the clearances and the things of actually building these substations. How did this installation come into not only selecting your arrestor, but what do you have to do besides selecting your arrestor? What do you need to consider? Well, conductor spacing and clearance. So that's in C62.82.2, and that is basically determined based on your BIL. They're usually baked in. So a BIL of 900 kV will have a specific amount of spacing and clearance requirements. It's important to adhere to these, of course, because if you violate those, your risk of flashover at those locations is significantly higher because you don't have the benefit of that insulating air. The next is leakage distance. So there are pollution classes that are described also in the same standard, and these go from very light to very heavy. And this is something like having an arrestor and a substation on the coast. You get a lot of salt spray that will actually coat your insulators, and your insulators can degrade and not have as good of insulating properties. Same thing if you're next to a factory or maybe a lot of homes and there's lots of potential pollution in the air. There's, like I said, very light to very heavy. Depending on that class, there's a larger separation distance needed, and those are actually usually found. The leakage distance is in the data sheets of the arrestors. And the last thing I wanted to cover was elevation impacts. So if you're building a substation up in the mountains, the air is thinner, and thinner air is less insulating. You can actually see a 20 to 25% decrease in the insulating properties of air. And so there is potential that you'll need to look into an even higher VIL or more arresters or a lower MCOB arrestor to make sure you're really protected, because it's not going to behave like it would at normal sea level. So, time
All
for
right. Well,
Q&A.
yep. Thank you very much, Joe. Very informative. I think that was a great presentation talking about our coverage on installation coordination. We're going to open up the chat now for questions. So if you have a question, please note it in the chat, and we'll do our best to address it. Checking the Q&A as well. So I don't see anything yet in the Q&A either. So we'll give everyone a few minutes to think if there's any questions on the presentation that you have. Maybe while we're waiting, so in our poll, we noticed that from a popular standpoint that the raising the MCOB was incorrect, right? We wanted to lower that MCOB level, and that wasn't the popular choice there. Joe, can you elaborate a little bit why lowering MCOB rating of arresters helps with our margins?
Yeah, so like I mentioned before, in those equations, we're using the residual voltage as the denominator. So if that value gets lower, then the margin goes up. That's just the math reason. What is the actual physical reason? Well, residual voltage is the voltage that the arrestor is letting through. So if you have a transformer that can handle up to a 1300 kV wave, a 1300 kV peak, and you let through 800 kV, let's say, well, that's going to be a certain percentage of that 1300 kV rating. Well, if you let through less, then you have less of a risk of that wave doing anything dastardly to your equipment. So as you decrease the amount of let through voltage, you are lightening the load of the wave survival, I guess, that the equipment has to deal with. Like I said before, just because you have a 1300 kV VIL and you have a 800 kV let through or a 500 kV let through, that doesn't necessarily mean you're not going to have flashover. It's not like, well, one number is greater than the other, so therefore it's big enough. That's not necessarily how it works. You just have significantly lower chances of a flashover happening.
Okay. Yeah, very good answer. Thank you, Joe. A couple other questions. We have a lot of questions coming in. I really appreciate your feedback. So this is awesome. Dave Lewis is asking, is C62 the primary standard for reference to this topic?
So C62 is very broad. It's C62.22 and C62, I have to remember now, I should know this. C62.22 and C62.11 have to do with arresters in particular. So things like energy ratings, things like their classes, the information on how their separation distance matters and what their protective ratios are. The C62.82 1 and 2 is installation coordination as a whole. It doesn't go into specifically about arresters, but it starts talking about things like BILs and conductor spacing. So it's multiple angles. You know, the arresters are just the tools we use to achieve our installation coordination and protect ourselves. But installation coordination is more than just arresters. It's also your conductor spacing, your BILs and BSLs and things like that.
Yep. Okay. Very good. Lots of questions coming in. For Kristen, yes, you're asking about the recording. The recording will be available this afternoon. Thank you, Del, for addressing that one. From James, what are some of the rules of thumb for arrestor application on the high side of transformers with a delta winding that is subject to backfeed from DER?
So let's see, on the high side of a transformer, that is typically you're not really going to see waves come through. There's not going to be an impact from anything on the low side of your transformer. I believe is what the question is. Any kind of generation on your low side, that transformer, which is something that I guess I could cover now. These waves can be very high frequency. They're moving very fast, so they respond to changes in impedances, treating them like a trampoline almost. There's a potential for a complete reflection when you hit these transformers. So any kind of low side contribution would not necessarily affect the high side. The high side would just see whatever wave hit. I'm assuming this is a distribution line. It's DER. You would have your lightning strike on your distribution line, and it would travel down to the location and just be the magnitude after its attenuation. It would be treated like any other traveling wave.
Yeah, and just to elaborate on that too, that's a good point, Joe. Transformers are your inflection points. They're large impedances, right? So we're going to see these waves kind of bounce and reflect off these impedances. And you're right, there isn't going to be a lot of propagation through that transformer. There is some, but small amounts. I think maybe you were getting at in your question was talking about if you have a delta high side. So what arrestor you use then? There are different MCOV ratings between the like an ungrounded and a grounded system. So with that delta high side, I would think you need to know a bit more about the distribution system you're connecting to. In the United States, generally every utility system that exists is grounded. I know there's a big caveat on that. It's not everybody. There's always an exception to the rule. There are some ungrounded systems, but most aren't. Most are grounded. So you would use a system that an arrestor that meets that criteria. And I think there's some guides out there from arrestor manufacturers that can give you some insight on what to use. Else we could discover that by performing an installation coordination study or a temporary overvoltage study to really zero that in.
Yeah, and add to that too, there's the ungrounded systems. You can see a full square root of 3 voltage rise, so you can see significantly higher temporary overvoltages on fault conditions that could even stand for a while, and maybe you don't have the protection to clear it because you don't have the visibility. In that case, you're almost always going to need a very, very highly rated MCOV or accept the risk that comes with the potential COV events.
All right, so very, very good. Thank you. Another question here, and I'll apologize. I don't want to mess your name up. So it's what is the study tools that are used to perform installation coordination studies, PSCAD or spreadsheet calculations?
So there are several tools that I've developed. It's really you can look at installation coordination kind of in 2 ways. There's the very, very heavily model dependent way, which is using things like PSCAD and actually going in and creating these waves and seeing the impact that these, go in and open that actual breaker and see PSCAD show you you're going to have a XXX kV spike coming your way. That is a possibility. In my opinion, a lot of times that's overkill unless you have a very unique case. The modeling time and the effort required to do a PSCAD model is just usually very significant, or instead of just PSCAD, any TP model, not to specifically pick on one. But I personally use a spreadsheet calculation that I developed by going through all of the standards, pulling out the equations that matter to me. And also, it's not necessarily all science, it's a little bit of art. The fact that we have to pick these numbers so early sometimes in a situation, and we don't have the full idea of what kind of impedances we have, the lines even coming in. We can calculate fairly accurately using a spreadsheet what the wave strength is going to be if we know the evident equivalent impedances, surge impedances, line construction types, things like that. But we don't, very regularly, we don't know that early in a project. So while there are equations to it, there's just a healthy amount of interpretation of go a little bit more conservative that we generally throw on as well.
Yeah, so and just to kind of sum that up, that's a very good answer, Joe. It kind of depends on your level of risk as well. So if we want to, if we know that we want to not spend a lot of time studying it, maybe we don't have a lot of the input that's required maybe early in a project and we need to get something ordered. We can do some high level calcs. We can keep it relatively, maybe we're a little conservative, but the study is a little less expensive. But the PSCAD, the more transient modeling work tends to be much more expensive, much more in depth. But it's kind of the quality of the data coming in affects the quality of the outcome. So if we don't have real data, we don't have nameplate data yet, this equipment's being built, then sometimes, maybe taking the conservative approach is smarter and better for many applications. So Adam, question, we frequently use utility recommended arrestor sizes for high side arrestors on transformers. Is there a particular scenario or voltage level where that can maybe get us in trouble?
So if the utility recommended arrestor, generally they've really got their act together. They really, really know because they're obviously ordering these in bulk. They have just as much, way more equipment generally at stake. And so they're typically application guides from utilities are very good. Just the important thing to notice is really when you're working on, maybe you've got to replace it it's or that vendor isn't available, you need to get a new vendor, or maybe something happens to it, it itself gets struck by lightning, or it breaks somehow, you need to replace it. It's very important to meet or exceed those ratings, right? You don't want to go down in energy rating because there's reasons for that. You don't want to go down in MCOV. You don't want to necessarily go up in MCOV. So I would generally, a lot of when my learning journey on this topic was happening, I did reference a lot of utilities as well, because sometimes they had a even more clear-cut explanation of why things happen the way they do. So if you have access to that, that's actually a very good tool to learn how to size these.
Yeah, and the utilities are going to have the benefit of experience, right? So they've been operating their systems for many decades, so they kind of know what works and what doesn't. But to Joe's point, sometimes especially with the boom of renewables, the boom of large loads, you may not have access to utility standards, or you may not have the access to the specific equipment. So maybe you'll have to, because you don't have the exact arrestor that the utility uses, you have to go buy one. You may need to meet or exceed that spec. So good point, Joe. Appreciate that. Next question here. Things are scrolling for me. So another question. I'd like to understand how to design a surge arrestor for 12.47 kV primary side, delta prime secondary, 480 volt. How tightly should we design arrestors for max protection? And just looking for feedback on that particular situation.
I think we could probably, that's a fairly specific example. I mean, send us an email. I'm sure we could talk about that in the future. But like we said before, the transformer doesn't necessarily matter if you're on the high side, as long as your separation distances are acceptable, and as long as your ratings are acceptable, you're not going to be conducting at nominal voltage, and you're not going to be so high that you're letting all the lightning through to destroy your equipment. There's the happy mediums there. The standard should be pretty clear. Again, transformer type doesn't really matter because of the fact that these events are going to be reflected off of transformers. So it's very much like a wall between systems that you're not going to see hardly any propagation through.
Yeah, and I would just sum it up that, hey, for any specific examples, there's a lot of considerations like we talked about in the call today. If you reach out to us, we'd be happy to help. It may be something that we actually need to do an installation coordination study for your system. But depending on the level of detail you need, maybe it's not too involved. So from Tim, if an arrestor is operated over its MCOV rating for a period of time due to system conditions, when I see that, I mean, maybe you're experiencing switching transients over the rating, so this thing's operating. Is there a method to determine what time duration it can sustain that over voltage prior to potential failure?
So that's TOV. That's the way I interpret that, and maybe that's not correct, but that is the TOV graph there. So if you're talking about a period of time, as in beyond seconds, and you're talking about potentially minutes or hours, that is, I generally, in a lot of my experience, I've seen situations like this of how do we protect for this scenario? And sometimes the case is you just can't. If it's going to be at a high value over its MCOV multiple of 1.2, 1.3 times, no rating out there is going to allow you to operate at that for an extended period of time, talking several tens of minutes. If it's just for a couple of seconds, there's the TOV curve that you generally can get from the manufacturer and find that. But I would, again, I've looked at it, even gone to the extremes and figured out a 21 kilojoule, I think, per kV MCOV arrestor, about the biggest I've ever seen. And even that wouldn't last for, in a certain situation that I was dealing with, for 30 cycles. And that was a very high over voltage, about 2.5, 3 per unit event. And so these things are, if they are meant to survive temporary over voltage with TOV, but just general over voltage, they're not able to withstand that.
Yeah, it's a very good point. I would kind of refer back to that TOV graph, which should be available from your arrestor manufacturer. Also, advanced engineering studies using PSCAD, we can look at situations. Essentially, we want to see where we exceed that energy rating. And I think we talked about that earlier in the presentation. So you'd have to do a study of your system to find out what that might be for different durations. And then we can select the right rating class arrestor. So, for example, to Joe's point, you have protection, your backup protection or breaker failure protection has a certain time period, maybe it's 30 cycles. you can perform that study and then confirm that the arresters you've selected are large enough and able to handle that. From Lucas, and we just got a few more minutes for questions. I'll do my best to get through. If there's any questions that we don't get to, we are going to stop at the end of the hour. Feel free to reach out to the email here from the link. That's marketing@cai-engr, and we'll do our best to follow up with you. From Lucas, less for surges and lightning, but operating at 138 kV and interconnected with the bulk electric system. We don't have control over the system voltage because that's maybe controlled by the system operators. And there are times it exceeds the system nominal normal of 1.05 per unit. The neighboring transmission owner cannot adjust their taps for 345 station to lower the voltage, so we're stuck with significant times operating above that 1.05. What are some of the considerations or justifications for allowing overvoltage above the nameplate ratings of equipment, breakers, switches, arresters, potential transformers that are rated at 145 kV when established or updating maximum operating voltage criteria? Lucas, that's a very complicated question.
I'll give
I would say
a quick one. I will say MCOV is not necessarily 1.05. A lot of times to see people standard, we go up 5% above. MCOV is your system's maximum continuous operating voltage. This is the kind of case that does need to be studied if you're regularly going 10%, 15%. Not speaking to breakers or switches here necessarily on continuous overvoltages, but for the arresters, you need to pick a higher MCOV and make sure that your new lower protection margins, because of the higher V residual, still protects your equipment.
Yeah, very good point. So yeah, I think when it comes to arresters, we don't tend to think at that small overvoltage. I mean, it seems like it's a lot, but at 5% overvoltage, most of our arresters aren't going to start to operate somewhere in the ballpark of like 25 to 30% over the voltage rating. But to Joe's point too, maybe if you're operating on the very ragged edge and then you have things like switching surges and lightning strikes, you're already at a high potential. Maybe you've degraded some of your insulation. I think there's studies that we can do to help determine maybe what we think the impacts to the equipment are, and maybe that's something you could use to work with your neighbors and set your own standards for voltage class equipment. All right. We have time for maybe one more. Kristen asks, can you describe the different voltage, or excuse me, can you describe the different consideration for arrestor sizing for delta winding versus Y windings?
Again, there's not really a consideration there. It's really, we're talking about the lines coming in. So it really goes back to grounding. We said before, is your system ungrounded as a delta, or what would that be? But really, it's the transformer is the wall that it bounces off of. So it's gonna, the waves do that. So you're gonna size your arrestor as if it's protecting basically the line end going into the station is more the way to think about it. It's the end of a line that can have its surge coming down it just before equipment. That's really the way to think about it. It's, and once it gets past that first winding, it doesn't matter really what the winding type is.
So I appreciate everybody attending our call today and our conversation. These questions have been excellent. So thank you for this. I think they have a few more questions that we would like to address. If you message out independently through the email, we'll give you some responses. Thank you again for attending. I really appreciate your participation, and I look forward to see you guys next month when we discuss dynamic stability, modeling, and analysis. So
thank you,
everyone, and thank you, Joe, for your presentation. Great.